This is my first example. Continuity of piecewise functions at a point. State whether the function is continuous at the value where the function rule changes. If continuous, state the three criteria. If not, state why. To start, let's remember our three criteria for continuity at a point. Our first one is that f of c must be defined. 2, our limit as x approaches c of f of x must exist. And last, we're going to put these two together. Our limit must equal our defined function value. So we're going to put the first two together and check. So to start, for this function, all right, for our first step, we're going to check if f of c is defined. Now, notice I didn't write f of c. I wrote f of 2 because that's the value we're looking at, where it changes. So f of 2, I'm going to try and take my x value 2 and plug it in. If I plug it in, I notice this is where when x is equal to, y is equal to 3. So f of 2 is equal to 3. That's a defined value. So I can say f of 2 is defined. All right. So put a check mark here. You actually have to have this explicitly stated on your end of unit exam. So if you want to box or check off whatever you need, I just met the first criteria. Step 2. I need to check if the limit exists. Check if the limit as x approaches that value we're talking about of f of x exists. Well, to check if a limit exists, I need to check from the left and the right. So first I'm going to check from the left. We're checking as x approaches 2 from the left. Well, I look up here when x is less than 2. That means we're going to be coming in from the left. So let's go ahead and I'm going to use 1 over x minus 2. All right, but then if I try and plug in 2, this implies that I'm getting 1 over 0, and that's not going to exist. So if I am trying to plug this in, I actually have a non-removable discontinuity in the denominator at x equals 2. So I can already say that the limit as x approaches 2, because it doesn't even exist from the left side. If I go and I check the right side, I'm going to use the other rule, x plus 1. Well, there I get 3. So now when I'm looking here, the limit from the left doesn't exist. The limit on the right does exist. So I have to say that our limit does not exist. All right, so we just failed the second criteria. Our limit doesn't exist because I don't have a limit. My limit doesn't exist from the left. So because the limit does not exist, I can say this function is discontinuous at x equals 2 because the limit as x approaches 2 of f of x does not exist. All right, so right here I'm going to box this. This is my final solution. Notice I said that if continuous state the three criteria, we proved one of the criteria wrong. If not, state why. I stated why. I stated that it's discontinuous. I stated where it's discontinuous. And I said why. All right, so I said what, where, and why. Now, I'm going to have you guys right now go ahead and you can pause the video to try this problem, and then I'll go through a solution. So this is a you try, pause it, see what you get, and then we'll go through. State whether the function is continuous at the value where the function rule changes. If continuous, state the three criteria. If not, state why. You can also pause if you get tripped up, watch, and then pause again and work through. So I'm going to say pause right now. And then after you're done trying it, you can come check the solutions. All right, now what I see when I look at this function is we have two places where the function rule changes. It changes at 0 and it changes at 1. This means that I need to check the continuity at both 0 and at 1. So this is a little different from the last example. We're checking continuity at two different points right now. So we're going to go ahead right now, and I'm going to do one at a time. So I'm going to start with 0. So the big idea here is check both points. I'm checking both points where the function value changes. All right, so let's start with x equals 0. All right, first, I need to check if f of 0 is defined. All right, if I go ahead and do that, I'm going to try and plug in 0. I just look in my rule where I'm allowed to plug in 0. Oh, when x equals 0, y equals 3, so f of 0 equals 3. So I can say f of 0 is defined. All right, we met our first criteria for continuity. Now let's check the second. I need to check the limit as I approach 0, and let's see what happens. Well, the limit as x approaches 0, I actually wrote this rule wrong. We got to go ahead all the way back up here, and we should have x squared minus x in the denominator. I didn't write that right. All right, so this is our actual rule right now. So what we're going to do, then we got to check the limit as x approaches 0. Well, I'm going to use my rule up here because this is saying around x is not equal to 0, but we can still get near 0 by looking at this function. So I have x, or this rule, x cubed minus x over x squared minus x. Well, if I apply direct substitution, I get 0 over 0, which means that I have to factor. So let's go ahead and factor. All right, this means we have an indeterminate form. All right, so what I'm going to do is let's factor. In the numerator, I'm going to take out an x and be left with x squared minus 1. Take out an x in the denominator, x minus 1. All right, well, I can still factor the numerator again. Just keep carrying your limit down. X times the quantity x plus 1, x minus 1, all over x times the quantity x minus 1. All right, well, let's cancel. We were going to remove these discontinuities. I'll remove this discontinuity, and I'm left with the limit as x approaches 0 of x plus 1. Now I can apply direct substitution, and I get 0 plus 1, or 1. All right, so my limit exists. All right, so the limit exists. We met criteria 2. So the limit as, it should be lowercase, x approaches 0 of f of x equals 1. So it exists. All right, we met criteria 2. But now for criteria 3, I'm going to put steps 1 and 2 together. Well, I have to check if the limit as x approaches 0 of f of x equals f of 0. Well, doing that, back in step 1, I found that f of 0 was 3, all right? I found that the limit in step 2 as x approaches 0 is, or as f of x, is 1. These are not equal to each other. So I just failed the third criteria. So I have to say this function is discontinuous at x equals 0. All right, so I said what? I said whether or not it's continuous. I said where. And now I'm going to say why. Because the limit as x approaches 0 of f of x is not equal to f of 0. So let's make yourself a quick note here. I have to say what right here. It's discontinuous. I have to say where. And I have to say why. All right. This concludes the first video, continuity, or not, oh, no, it doesn't conclude. Whoops. All right. I didn't even finish the problem. All right. Now, so I checked when x equals 0. I still have to check the other point where we have a change in the function rule. I didn't even check x equals 1 yet. It's a mistake. All right. Now, so when you check x equals 1, it's the same process. So let's do our first step. We got to check if f of 1 is defined. All right, let's go ahead and do that. So, well, if I try and find f of 1, I'm going to go to my piecewise rule. Well, if I plug in 1, I get 2, so f of 1 equals 2. All right, so we can say f of 1 is defined. Just put a check mark. We got that checked off. All right, step 2. We have to check if the limit as you approach 1 of f of x exists. All right, now we're going to still use this rule here, but x is going to be approaching 1 this time instead of 0. So let's check it. The limit as x approaches 1 of x times the quantity x squared minus 1 over x. Oh, whoops. Actually, so right back over here, we already factored this and got it all the way down to x plus 1. So I'm still going to use the same thing. The limit as x approaches 1 of x cubed minus x over x squared minus x. But then I already simplified this all the way down to just x plus 1. All right, so I don't want to redo work that I already did over here. So I already simplified it down right here. So just plug in 1 and I get 2. 1 plus 1, 2. All right, so now I can say the limit as x approaches 1 of f of x exists and equals 2. All right, so we just met our second criteria. F of 1 is defined and our limit exists. So now for step 3, all right, what I'm going to do is check if f of 1 equals the limit as x approaches 1 of f of x. Well, yeah, it does, because back in step 1, I found that f of 1 is 2. In step 2, I found that the limit is 2. These both equal each other, so our function value is equal to our limit. So we just met the third criteria. Yes. f of 1 equals the limit as x approaches 1 of f of x. All right, so this time I met the first criteria for continuity. I met the second, my limit existed, and then I showed they were equal to each other. So I can say this, I met all three criteria. This function is continuous at x equals 1, and then these three criteria count as your y. You just show me why. You proved the three criteria, or we proved the three criteria. So it's continuous at x equals 1 because it meets the three criteria. This concludes the first video on continuity at a point. If you have a specific question, I need you to please message me on Remind about that question.